Okay, so I'll briefly introduce myself. My name's Tom Trevethan. So I work for a company called CommerceBlock, and I've worked there since the beginning of 2018, which is nearly 2 years ago. And CommerceBlock is a startup. We're essentially a technology provider, a software company. When I joined, it was just me and Nick Gregory, who's like the CEO. And since then, we've grown to a team of about 11 of us in total. Yeah, so we've got a variety of different kind of projects that we're working on. But the main thing that we've been doing in the past 2 years, which was our kind of major client, was to build this gold-backed token on a sidechain. So this was where this has been our focus for the past couple of years, and they essentially paid us to do this. The motivation for doing this because they wanted to, well, for various reasons. I can go into some kind of detail about some of the choices that were made. Yeah, so essentially I'm moving, go straight into this kind of idea of tokens, and specifically asset-backed tokens. So what it really means to have some physical asset like property, real estate, or equity, and have a token. I mean, what does token really mean? I mean, token implies that it's ownership of something that can be transferred between people easily without too much friction. There is a kind of obviously a big criticism of the idea of having blockchain-based tokens is that these are centralized things, either gold in a vault or someone has a key to the real estate. And what's the value of having these kind of things as blockchain tokens? Why not just use spreadsheets, databases? So I'll go into this a little bit, maybe make a bit of an argument as to where the value comes from there. And so I gave a talk a few months ago, and I had these slides in, partly because there were some people in the audience like Peter Todd and Giacomo Zucco who have these arguments about what blockchain is and is it time chain. So I put these slides in to maybe try and get a bit of reaction. I came up with these facts which may be controversial or not. The first one was that as far as I'm concerned, a blockchain is not a database. It can't really be compared to a database. It's not meant for storing records. It's meant for proving the state of a database. So in Bitcoin, the UTXO set is actually the database. It's the list of who owns what. And the blockchain is something that you use to prove the state of the UTXO set to someone else. And I really like this definition here. Blockchain is only proof. It's cryptographic proof of the specific state of some ownership records. So another one, Git is not a blockchain. People always kind of tend to cite Git as an example of blockchain, but this is not true either, because Git doesn't have any rules about what is valid and what's not valid. I think fundamentally what blockchain does is verify to someone that a certain set of rules are being followed. And finally, this one, blockchain is not a time chain. I know people now like to use this word time chain instead of blockchain, because blockchain has been massively abused and people are getting a bit tired of that term. But as I'll go on to explain a bit about why I don't think time chain is not a very useful word, and that time chain implies that you're just proving the existence of things, whereas blockchain is more a proof that things haven't happened as opposed to things have happened. So it's not just a time stamping system. The whole point of the blockchain is to prove uniqueness, so to prove that things are only spent once. So in order to do that, and this quote from Satoshi's white paper, that the only way to confirm the absence of a transaction is to be aware of all transactions. And this is why blockchains are, I think, very powerful concept, but at the same time very poor at scaling, because you need to verify everything.
So this is this feedback loop. Like you have to have an ordered set of transactions. It's not just proving something hasn't happened. You need to know the time intervals of which things have happened to work out what the current state is today.
Yeah.
So I think there's like this feedback loop between the timing and the uniqueness.
But I mean, really, if you fully verify said Bitcoin blockchain, what as a verifier, you want to confirm your ownership. So really, I mean, as a user, the only reason you want to verify the full Bitcoin blockchain is to verify that you've received the transaction that's paid to you, and that transaction is unique, so that only you own that Bitcoin, no one else owns it, and that you have this global view of basically that there's only a single state. So in this kind of the view of what blockchain is, so blockchain along with the private key that controls nowadays is a proof that you own. I can prove I own Bitcoin because I now have a private key and I have a Bitcoin blockchain. I can prove that I own the Bitcoin, and that this proof of ownership can be used. You can use the same model for other things, even if you don't have physical control of those things. You can define ownership in a way that individuals can prove that they own something, and if you have a global state that everyone can verify that there's that ownership is unique, that this is actually a valuable thing, and that there's this kind of nice example of where this kind of thing can be useful, even if you have a centralized thing, for example, a stock in the Dole Food company. There was something went wrong with the company, and they basically recalled all the shares, and all the shareholders basically kind of turned up, and it turned out that there was 60% more shares issued than there was stock in the company. And so everyone's shares were actually worth a third less than they thought, because they basically issued too many shares. And obviously, if you've just got some entity which is issuing shares without any way to verify that, that there's a fixed supply of shares, and to independently verify your ownership against everyone else's ownership, which you can do with a blockchain if you are sure, if you're confident that that blockchain is unique, then you can prove that your ownership or your share of the ownership is completely unique. So this is kind of this is what we want to do. We want to be able to utilize a public blockchain to prove ownership of something. So the kind of the most obvious way to do that is to go to the most secure blockchain that there is, the Bitcoin blockchain, and you could issue tokens directly on the Bitcoin blockchain. This is done by several kind of protocols like Omni, Counterparty, things like that, where you can verify your unique ownership of the token by verifying the Bitcoin blockchain that it's unique and valid, and you verify some additional rules to prove the uniqueness of your ownership, and additional rules that allow you to transfer that ownership via a Bitcoin transaction. So, so most famous of these is Omni layer, which has Tether issued on top of it, and this is the most kind of valuable and successful tokenization ever in this new field. So I'm not quite sure how much Tether there is issued on Omni layer, but it's in the billions of dollars worth. So this is obviously a successful method, but it's a big problem in that it can't scale to. You can't have a large number of issuers, because every single token transaction has to be a Bitcoin transaction, which doesn't scale quite large transaction fees, and you're never going to be able to issue more than a few tokens. So you could use a different public blockchain that had more, kind of block space if you wanted. Say Ethereum was kind of built on this idea. You can issue tokens on Ethereum. Then kind of this has been made more kind of user friendly, and that's the model of Ethereum now. People can issue tokens, but the same problem is still there, and that even if, well, obviously, firstly, Ethereum's not as secure and immutable, so it's second place if you're going to pick a public blockchain to issue a token on. And because of the scalability issues with Ethereum, it's very difficult to verify and fully verify. And this is really a fundamental problem with issuing tokens on a blockchain that are not the native unit of that blockchain which powers the consensus. And that you now basically, to verify the uniqueness of your token, and to verify your ownership of the token that you care about, you also have to verify the full history of every single other token that's been issued on that platform. So if you issued a token on Ethereum and you want to verify your unique ownership for that token, you have to verify everything that's ever been issued on it. Every single computation that Ethereum has ever done, every single CryptoKitty transaction, you also have to verify that as well in order to verify your own ownership. So this really doesn't scale. So this moves on to basically our model, which is slightly novel, in that when we're looking at, say, tokens that are issued, asset-backed tokens, where there is inherent permission in the issuance of those tokens, which is always the case for any kind of security token, and in the case of our client, this gold-backed token, every single transaction has to be permissioned. So in this model, our model, we think it's much more scalable that you have the issuer control their own blockchain. So in this case, basically, if you have a single token, say you're tokenizing equity in a company, or in the case of this gold-backed token, you have a single blockchain for a single issuer, and that issuer basically is in charge of creating blocks. Then they are able to apply policy to the transactions that they add to blocks. Yet you can still derive the uniqueness of this blockchain from Bitcoin's global state. So I mean, if you just had a single a blockchain that's controlled by a single entity on its own, it's pretty kind of not. I don't think it's completely redundant, because the blockchain could be publicly verifiable. So everybody who anybody can publicly verify the state of the blockchain, and you have a single entity signing blocks. But obviously that entity can kind of create as many versions of that blockchain as they want. They can completely rewind, reorg, double spend as much as they want. So you completely trust the block signer. So, well, in that case, your proof of ownership then is not valuable, because the block signer is in complete control of that proof of ownership. But in this model, if you can actually derive uniqueness from Bitcoin, and you can prove that there's only a single possible history of state in this second permissioned blockchain, then you have all of the properties of issuing a permission token on a public blockchain, but without the scalability issues. So, yeah, you derive this as basically it's permissioned, centralized, but it's immutable in the fact that it's fail secure. So the issuer cannot double spend you, because your uniqueness, yes, is backed by basically uses Bitcoin's immutability. So I'll go into a bit more kind of detail about this. So to implement this kind of model, we took the Elements code, which is used for Blockstream's Liquid. So Elements is basically the Elements project is forked from Bitcoin, the main Bitcoin core client, and it was changed in order to make these what are called like federated sidechains. So have basically a number of private keys which sign in multi-sig essentially to validate a block and add it to the blockchain. In this model, so you have a fixed number of block signers. So in Blockstream's Liquid, they have these 15 block signing nodes all around the world, distributed. In our model, you have separate block signers, but this is only for kind of redundancy and security. All of the block signers are under the kind of legal control of the asset issuer or the token issuer. So the way, basically, this is kind of an overview of kind of architecture. So you have private infrastructure where you have private keys for doing the block signing, controlled in hardware security modules. This is all controlled and owned by the asset issuer, but then the blockchain itself is publicly verifiable. And then also, which I'll go on to talk about, MainStay and how Bitcoin plugs in and how users can independently verify the immutability of the sidechain. So this model allows us to do a few things to do with transaction permissioning, and these came partly from the requirements for this project. This gold-backed token, and this is why for this project we had to fork elements to add these features, because elements didn't have these things in. So at the moment we're kind of talking quite a lot with Blockstream about moving a lot of the features we've added back into the Elements project, so that we don't have two separate kind of forks. I mean, some of the things that we added when we started the project, Blockstream have gone and done anyway, kind of multi-sig issuance and things like this. But essentially, the thing that we can do with our model is that we can actually enforce, because the issuer controls all of the signing nodes, we can enforce basically on the policy layer. We can do whitelisting, freeze listing. We can control the way issuance is done. And the way we implemented this is everything can be actually controlled via the blockchain itself. So we can have basic wallets that with the wallets with a certain key are able to add users, for example, just via the wallet. So this basically, we added all this functionality to now allow us to build this permissioned asset-backed chain.
What does the whitelist mean?
So it's basically you have to, if you want to receive a token, you have to be KYC'd. So you basically you download a wallet, you basically export like a XPub or a list of addresses from that wallet, and then you go through KYC to whitelist those addresses, and then those addresses are allowed to transact with.
So I suppose with Liquid, when it has the 15 signers, they are all whitelisted.
Yeah, well, it's a different thing. I mean, in Liquid, there's no transaction permissions at all. So, although you've got 15 signers as default, they could, if they wanted to, censor transactions based on some criteria. If law enforcement put pressure on them, for example. But by design, in Liquid, there's no permissions for transactions. There's no whitelisting. They do actually implement whitelisting for they've got this security token function that they're building now, but they're doing whitelisting in a different way. They're doing whitelisting with a multi-sig. So essentially, you have a whitelist or KYC server who has one key to a 2 of 2 multi-sig, and then they co-sign if someone's on the whitelist, and they don't if someone's not on the whitelist.
So what's the purpose of the whitelist here?
It's to restrict. It's to obviously you're not allowed to transact unless you register somehow.
Because on Liquid, anyone can transact.
Anyone can transact, but what they want to do is they want to do restrictions for like certain. They want to do like security tokens on Liquid. Security tokens have to have like a KYC, restriction, so that only registered users, only KYC users are allowed to transact that token.
So the single question is like, if I'm a user,
Yeah.
now I'm interacting with one of your wallet, right? So let's say you have 10 or 15 wallets.
Yeah.
Interacting with your chain. I'm a new user, I don't know anything about crypto, but I'm really interested to buy a token. So I need to go through a KYC and then come to your wallet, alright? Or does the whitelisting mechanism is actually
you whitelist it, you get the wallet, you generate your own private keys, you then export a file which contains a list of your addresses from that wallet.
So the reason I'm asking you that, sorry to interrupt you, just to add that one more statement. So if you go to Binance, it won't ask you to do any KYC if you're not doing any transactions. Not all the Binance, but
yeah.
Most of the Binance exchanges. They won't ask you to do the KYC if you're not transacting more than a certain limit.
Yeah.
So if you pass that limit, then you need to go through the KYC.
Yeah.
That makes a lot of sense, but otherwise it's a barrier of entry.
Yeah, of course.
If you need to come and interact with our chain, then you need to do like XYZ.
Yeah.
And I don't know that. Because that person doesn't even know what is a token, right? Because it's new.
Yeah, of course. Yeah. Well, yeah, it's definitely a. I'd love to live in a world where there was a lot less KYC requirement, but unfortunately, that's the world we do live in.
But your whitelist is optional, right? I mean, if you want to issue an asset on here and
Oh,
don't
and principle, yeah, of course. This is all configurable, so
Ah.
anyone can choose whether to use this. This particular issuer needed a whitelist.
Alright, okay.
So
That
yeah,
makes sense. That makes sense.
they needed lots of other things. There's lots of other complexities with this. We had to really kind of come up with a
So
lot.
this is not a default option for your chain. It's
Oh no, of
just
course not. No,
solutions.
no.
Okay.
It's basically what I'm saying is that we added functionality to allow basically policies to be applied at the transaction layer. So but these policies aren't consensus rules; they're policy rules. So it's determining which transactions can basically be added to blocks and which can't. So essentially, yeah. So we did this for this project DGLD, which it had a lot of kind of quite novel requirements. One of the things they added was like a demurrage fee, so that the gold is in the vault, but there's a demurrage fee. So every year, your entitlement to the gold reduces by a small amount. Also, there's a mapping. So we really tried to make this as kind of everything as verifiable as possible, so that you can, within your wallet, you can basically see which every individual gold bar, which has a unique serial number by the refiner that created the bar, and that maps directly to a token type on the blockchain. And you can verify within a wallet. You can actually see exactly what you own directly. So yeah. So
just on that last project, so that sounds very similar to a project BitGo worked on for the Royal.
Yeah. They
Did you
did
speak to those
RMG.
guys?
Yeah, we spoke to them quite a lot actually. So RMG. RMG Gold was started quite a while ago, and BitGo created this. BitGo created a whole platform called Prover for it. They had some strange kind of design decisions. I think they kind of like made it semi-permissioned, semi-proof of work. Because I think that the people that were involved in the project wanted it to be kind of a more permissionless, decentralized blockchain, but I think the people that are behind it wanted a permissioned blockchain, so they kind of met in the middle somewhere. Yeah, unfortunately, I think that project kind of got into trouble with the UK regulators. So it's being backed by the Royal Mint Gold, but I think there were some problems with the HMRC, which kind of scuppered the project. But I think quite a lot of people were going on it. I think BitGo spent like a couple of years kind of working on this. But yeah, they developed this Prover platform, which was based on BTCD, which is the Golang Bitcoin Core client. But anyway, this project's now live. It's got like $25 million worth of gold tokenized on it. And yeah, it was kind of, everything works. But I'll go on to talk about then why this permission blockchain, we can actually, make it provably unique, and it's proved as immutable as Bitcoin. So we need, so like I said, so any particular permission blockchain where anybody can sign blocks, that you're under the complete, basically, trust of those block signers, because they can create 2 versions of the history of the chain, and they can then perform like a double spend against you. So what we need to do then is have a globally objective state, Bitcoin, that doesn't rely on trust in the asset issuer. So it's not possible for the asset issuer to actually to change the history of the blockchain, to change, to go and change the ordering of transactions in any way. So we go to Bitcoin because nothing is as immutable as Bitcoin, and that proof of work basically means you can get this global objective state without trusting anybody. And the fact that you don't trust anybody for this makes a proof based upon Bitcoin much more valuable. So how do we do this? So you kind of think, okay, we just timestamp into Bitcoin, take some state of the asset-backed blockchain sidechain, and commit it into the Bitcoin blockchain. But this is not sufficient to, you can prove that basically that data existed, but you can't prove anything else about the kind of uniqueness or provenance of that data. So just a bit of an aside, I thought I'd just maybe quick kind of history of time stamping. I thought there's some quite interesting things about, the first ever trustless timestamp was done by this guy Robert Hooke, who was a physicist slightly before the time of Isaac Newton, and he wasn't a very popular guy, didn't really trust anybody, and so he basically came up with this technique to prove this idea he came up with, which I don't know if you remember Hooke's law from school, where you take a spring, and that the force and the tension of the spring is proportional to the extension. And so he took this, basically, he published this book in 1676, and he included this string in it. And then 2 years later, he published his theory about the spring, and then revealed that this string was actually an anagram of this tensio sig vis, which is like Latin for as to the extension is the force or something. So basically, he did this commitment, a cryptographic commitment, published it. It was widely disseminated, and then 2 years later, he then revealed the commitment he made to prove that this piece of information existed 2 years previously. And then quite a few years later, these guys, Stuart Harbour and Scott Stonetta, published a way to do this with proper cryptographic hashes. I think Robert Hooke's method was probably the first ever cryptographic hash function. But these guys came up with this system to do timestamping in a similar way, but in a much more efficient way, a much more scalable way. So in this way, they'd actually take documents, digital documents, create cryptographic hashes of them, and then basically, create a tree of these hashes, and then every few days they would publish the root hash in the New York Times, and essentially anybody could then verify that something existed. So they wouldn't have to publish a hash of loads of documents, just publish one hash, and you could then go and prove that your document was timestamped at that time by checking against the root hash in the newspaper. And given this newspaper is kind of widely circulated, it's the New York Times, you can be quite confident that something happened a certain date. and to kind of try and con people that something didn't happen, you'd have to forge New York Times, collect every word. There was this, I found out about this by this article which said basically the world's oldest blockchain has been hiding in the New York Times since 1995, but I disagree with this statement. I don't think it's a blockchain. This isn't a blockchain because it doesn't have any rules that govern the validity of what is actually committed. So this was, the first description of a real blockchain, the Satoshi white paper, and he actually cites Scott and Stornetta 3 times. There's only 9 references in the white paper, and 3 of them to Scott and Stornetta, so it was obviously very influential on Bitcoin. People use Bitcoin for doing this trustless timestamping now, making commitments into Bitcoin transactions. And there's quite a lot of services. The most famous is Open Timestamps, where you use these calendar servers to compress lots of commitments into a single commitment that makes it kind of very scalable and efficient. But fundamentally, timestamps don't achieve what we want to achieve, which is to prove uniqueness of the sidechain and the single unique history of the sidechain. So the reason, I'll kind of go through why this doesn't really work. So I can commit something into Bitcoin, the Bitcoin blockchain, and then go back and prove later on that this data existed at this time. But I can commit lots of different things into the same Bitcoin block at the same time. And I could selectively reveal one of these later, depending on what was most convenient for me. So another, so if I did this for, imagine we've got a sidechain here, I could commit the state of that sidechain into the Bitcoin blockchain periodically, but there's nothing stopping me as a bad, block signer from creating a completely alternative version where I've double spent someone. So in one version of blockchain, I'm revealing to one set of people, another version I'm revealing to another set of people, and then perform some kind of double spend against them. So the way to get around this is to basically use, again, the uniqueness of Bitcoin, uniqueness of Bitcoin outputs. So this is an idea originally by Peter Todd. Basically he called it a single-use seal. So the idea is that you identify as a globally unique kind of ID, which is a transaction ID, and that then something you commit to that, you can prove that that commitment is unique. So essentially you take the Bitcoin transaction ID, you publicize that as the location for where you're going to commit something, and then you can prove later on that that's what you committed to that, to a transaction that's spent from that transaction ID is unique. So essentially, so this is basically the kind of key, I think, to really what blockchains do. The only way to confirm the absence of a transaction is to be aware of all transactions, so that you know that every single transaction ID is unique, and every single output there's no double spends. So this is essentially what we do for this MainStay protocol, but we take this idea of a single-use seal and just extend it in time. So the first step is we have a transaction ID, which is kind of like a base transaction ID. Then we commit that transaction ID to the Genesis block of a federated sidechain. Then that sidechain blocks added to it by the federated blocks owners, and then periodically, could be every 10 minutes, every hour, we then commit the state of the sidechain back into a transaction which spends from the original transaction output, and that this transaction basically only has a single output, and this transaction only has a single output, and then we spend from this transaction to another transaction which contains a commitment from the sidechain as extended. So this is rules extended, and then we can verify if this rule is followed, that every single one of these transactions only has a single output. We can verify that there's only a single possible history of the sidechain. And if this becomes a new rule that we use when we verify our ownership of a UTXO on the sidechain, we then basically have a proof of uniqueness. So we now the sidechain, the history of the sidechain is as immutable as the history of the Bitcoin blockchain.
Excuse me. The transaction that you mentioned on the Bitcoin, how much you make a transaction, like every epoch?
You can make it every Bitcoin block.
So you're going to send some Bitcoin on every block?
Yeah, so Bitcoin is just sent here. Someone or a federation, essentially, and depending on the model, the federation basically controls this Bitcoin output.
So your block corruption is related to a transaction made on Bitcoin and getting
Yeah,
back?
you can have, I'll kind of show you, you can have more frequent blocks on the sidechain. However, these intermediate states don't have the same confirmation guarantees as the ones that have commitments into the Bitcoin blockchain.
So more or less these are the checkpoints?
Yeah, pretty much, yeah.
Okay.
So this model is obviously, there is there is trust required in this, so requires key custody. Someone or some collection has to control those outputs and control the addresses, the public keys that control those outputs. So in one model, it makes sense that the Federation control those keys and that they're responsible for signing the Bitcoin transactions, as they are for producing the sidechain blocks. So although you're trusting some entity to do these commitments, it's kind of fail secure. So the verification is trustless. So you're relying on the block signers or some other entity to keep the system going, to keep performing these attestations. But the verification is trustless. So when you do this verification, you essentially do full verification of Bitcoin, full verification of the sidechain, then you run this additional MainStay daemon, which does verifies this sequence of transactions of Bitcoin, and then your wallet will tell you when your transaction's been confirmed. So we actually have like implementations of wallets which do this confirmation. One of the things that is quite nice about having this rule that every transaction only has a single output means you can actually use SPV verification, which, you know, there's lots of arguments whether SPV verification is useful or secure, but it does add proof of, it does prove that there's proof of work backing up this sequence of transactions. And so in our kind of wallet, we actually have two types of confirmation for a transaction. So this is a fork of Electrum, which basically connects to two blockchains. It connects to the Bitcoin Electrum network and also the sidechain servers. And so it's verifying both Bitcoin block headers and SPV proofs of the MainStay attestations, as well as verifying the sidechain transaction history. And so you actually get two confirmations. So you get the number of, this transaction here has kind of 654 sidechain confirmations, because the sidechain blocks are a lot more frequent than the Bitcoin blocks. And then you also have a number of Bitcoin confirmations. So yeah, so that's basically the basic idea. But again, this doesn't really scale. And the issue is, obviously, if we were going to take this model of having a separate kind of sidechain for every asset issuer, it also wouldn't scale, because maybe you've got thousands of different assets, thousands of different sidechains. You can't all do this into Bitcoin because there's not enough space. So we came up with, I don't know if anyone's heard of VeryBlock, and that VeryBlock a chain that's doing a similar kind of thing, but they are in a way there's been lots of criticism for VeryBlock because they were for kind of spamming the Bitcoin blockchain, but they're doing a kind of a decentralized version of this, but because it's decentralized, it's very inefficient. People basically compete in order to get these commitments into Bitcoin. And so at one point, I think about some point last year, I think 80% of all Bitcoin transactions were VeryBlock transactions. And lots of people were kind of very upset about this and its inefficiency. So this idea of MainStay is a lot more efficient than that, but obviously it relies on a single entity performing these commitments. But again, so there is a scaling problem here. So we basically came up with this idea to scale this and compress it in a very, very similar way that Open Timestamps does this. But in our case, the only difference is that in order to maintain this property of uniqueness and immutability, you always need to have a commitment in the same position of a Merkle tree. So basically the idea is that now we can basically compress lots of different commitments from different sidechains or different users, entities, into a single commitment into the Bitcoin transaction chain. And we preserve the property of uniqueness and immutability. That commitment goes into the same position in the Merkle tree. And we call these Merkle leaves slots. So the idea is that each slot is exclusive to one user, and that through, we operate the service, we construct the Merkle tree, do the Bitcoin transaction, we handle the Bitcoin side of things, and the user basically has exclusive use of a single slot, and they can get this proof of uniqueness, this proof of single history, without trusting us. So, a big part of this, we need to make this secure. If we're running this as a service, we need to make sure it's reliable. Like I said, it's trust is verification, but obviously if we lose the keys to the Bitcoin outputs or anything, then obviously the service doesn't work anymore. So we've taken a lot of effort and care to do this in a kind of secure way. So we have all outputs are all kind of multi-sig outputs with keys stored in different locations. All the signing keys are basically generated within hardware security modules. We worked with got a partnership with this Swiss company called Securasys, who manufacture these hardware security modules, and we did some work with them on, as I'll go into how we do the commitment. We had some tricky issues on how we do the commitment, but they worked with us to customize their HSMs for what we needed. So I'll just do a quick comment about how we actually do the commitment. So nearly all of these other timestamping methods that use Bitcoin as a timestamping mechanism do op return. So they include the commitment just in op return, which is like a unspendable output in a Bitcoin transaction. Though we use a slightly different method. We use this pay to contract, where we can actually commit a hash to a transaction without using an op return. We actually embed it in the public key of the output, or the address of the output. So pretty much how this works is that this is the standard kind of pay to contract setup, where you essentially have a public key that you have derived from a private key, and then you basically commit to it by adding, so this is basically an elliptic curve point, and you add another elliptic curve point which is derived from your commitment. So then you can still spend, you can then pay Bitcoin to this address derived from this pub key, and you can still spend it because you have a private key, but you can also prove that you've made this commitment to the public key. So it's basically a way of hiding commitment, and you don't have to pay any extra money for your op return. And this just looks like a standard Bitcoin transaction. So if in the future people did get fed up of op returns and decide to soft fork them out or something, this would still not be a problem. However, we couldn't actually do this, and I mean, part of the my kind of learning experience over the past couple of years in trying to do real things. Previously, I was doing just kind of theoretical things and research. Is that, you know, when it comes to actually integrating, you can have all these kind of fancy cryptographic ideas, but when you actually have to integrate with people, it becomes tricky. One of the first issues we had was with we initially did a pay-to-contract system in the addresses of the sidechain outputs, but then when it came to, we had to speak to Ledger to integrate with Ledger, and doing this kind of key tweaking in the Ledger is a real pain. And we found with our partner Securitas as well, it was a real problem doing the key tweaking within inside the HSM. But we actually came up with another solution, which used basically like a BIP32 derivation path in order to embed the commitment into the address. So it's a slightly different way. So you've got, say, your commitment here, which is like 32 byte hash, and you actually derive this kind of massive HD derivation path from this commitment. And then you derive an address from your master private key based on this path. Then you can pay to this address, but then you can go back and prove basically the commitment is, or that this address is derived from this commitment. And this, we managed to work with the HSM provider to use this. So this is what's used on our current MainStay server. I was going to talk about some other things that we're now looking into doing, like document history, using this MainStay idea, say proving that a particular document only has one possible sequence of changes. This turns out to be kind of very important these days in a lot of fields in kind of scientific publishing and things, where there can be arguments over the sequence of changes that were made to like a very contentious paper, you know.
This is where you could use Git, right?
Yeah, I mean, but obviously you can also, we've also integrated with Git as well, because obviously Git, you need a way to, you can use Git for like document history tracking, but then you've got to prove the uniqueness of your Git repository as well. So it's like, obviously you can publish your Git repository, but then it's about proving that this is the only version of the Git repository that there is, and that this only has a single history. Because I could have created 2 Git repositories, and then I can, you know, show one to one person, show another to another person.
So your chain is only brittle to the liveness failure of a Bitcoin.
Yeah. So yeah, basically this is one of the kind of things we started working on now. So yeah, I mean that's I guess all I'll talk about today. We do have quite a lot of other projects going on. We have this idea called guard nodes, which is a way to incentivize people to run fully validating nodes of a kind of centralized blockchain to provide a kind of watching service. We're also working on this thing called chain cert, which is like SSL certificates for tokens and sidechains. But everything we do is is open source. And yeah, okay, so that's it for today. Thank you.
Okay, questions?
Questions?
Have you considered the difficulty rate when you considering taking the Bitcoin timestamp?
Well, it's something you always have to be aware of, because I mean, if you define your rule as in basically if you say Bitcoin is an objective state, so that there is one Bitcoin blockchain, it's always the one with the most work. Obviously, the difficulty is kind of not something you consider unless you start to doubt the security of Bitcoin. So obviously, if there's for some reason the value of Bitcoin drops a lot, the hash rate drops a lot, and it becomes a lot less secure, then the whole kind of model is questionable. You know? So all this is based on the.
So I'm more concerned about. I'll just rephrase it. So just goes through a client, right? The Bitcoin client. Just closing it out. So if I take all my some of the archive node and take all the headers and just try to spam your network somewhere or the other, and I can get that Bitcoin, the uniqueness part that I can break it, not breaking the Bitcoin, but the client. So I can just spam your network and then just drain the assets. But then your permission network, you can always go back.
Yeah. But I mean, all this does is just prove that. Yeah, it just proves that the secondary network, the secondary sidechain, can't be rewound.
So you're anchored to the Bitcoin. So let's say you're anchored to the Bitcoin security layer. If I'm attacking the anchor, the bulls, and if I'm spamming here, I don't have to worry about the Bitcoin. I don't have to.
Yeah, but you can't attack the anchor unless you do something to Bitcoin. So you could spam Bitcoin to prevent the.
I can spam a client with taking all this information from the previous. I can spin it up and I can spam your client.
But spamming the sidechain is not going to affect the anchoring to Bitcoin.
Yeah,
so
I understand that, but the assets are not sitting on Bitcoin. Assets are sitting on your sidechains. I want to drain the assets sitting on the sidechain, so I'm just making out that uniqueness thing, right?
Yeah, you could kind of spam the sidechain, do a denial of service attack on the sidechain.
The fallback is your permission, so you can always go back.
Yeah. So with the idea is that the issuer can not ever change the record of ownership. So the issuer can obviously.
Right.
The issuer owns the asset. So in this DGLD model, the issuer has the golden vault. But what we want to achieve is that the token holder has a proof of ownership that cannot be taken away from them, even by the issuer. So no matter what the issuer does, even though they control the block creation on the sidechain, that ownership cannot be taken away, and that the token holder will always have like an independent proof they can take to a court or to prove their ownership.
Question exactly regarding this point, right? So let's say on the sidechain, I have 1 ounce of gold.
Yeah.
Right? And that gets attested to the Bitcoin blockchain. And say the next attestation is 1 hour later.
Yeah.
15 minutes later, the evil sidechain operator decides to give my 1 ounce of gold to somebody else.
Or what they can do is they can't do that. The block signer can never take away an output you own, just like miners in Bitcoin can't take away an output you own. All they can do is go back to a different version of history. So if you receive, so basically what I would do is I would send you 1 ounce of gold, you pay me money in cash, then I'm the evil block signer.
Yeah.
I then go back.
Double spend me.
I go back 15 minutes, and then the output where I paid you, I now go back and create a transaction paying back to me.
Yeah.
And then I've then defrauded you out of.
What if you can delay it for some time, and
well,
then include it on the coming blocks later? So all this way I bribe the other people, and then I collude it, and then I take that money.
Yeah. So in that 15 minutes, basically, as the bad block signer, I can collude with someone to double spend against you. But then once the commitment is in Bitcoin, I can no longer do that without reverting the Bitcoin block or reorging the Bitcoin block.
Yeah.
So there's these 2 levels of confirmation. So you have the initial confirmation from the sidechain block signers, which you may not choose to trust if it's a large amount, but then you wait, half an hour before you get your Bitcoin
Okay.
confirmation, and then you have much greater certainty that
You can't roll
it,
back.
it can't roll back.
So you have some kind of fisherman or some kind of mechanism always checking the proof if someone actually misbehaved.
Well, really, everyone should be checking the proof. That's the model we want with blockchains, isn't it? That everyone verifies. The reality is people don't tend to, but in principle, I think that we should be building things that try and make it easy as possible for people to validate everything.
No, so something happened in sidechain. If I
Yeah.
have in Bitcoin, so you're like mostly like what I see is like an optimistic roll of theory. Like you just actually use a Bitcoin as a fallback, a security layer, and the final code of appeal you can always go back and take that timestamp and say,
Yeah.
hey, this is it, right? So someone actually has to see this sidechain all the time.
Yeah. So the user, like for example in our wallet, you would actually wait for the confirmation. So you confirm sidechain state, confirm the state in Bitcoin, and then you get this confirmation.
Right.
And until you get that confirmation, if it was a large amount of tokens, I would wait for that confirmation before I gave my cash.
And this confirmation is probabilistic. It's not really like.
No, but I mean the whole Bitcoin confirmation is always probabilistic, but then this is the only way to do it. I think they have an objective state which is
Right.
trustless, and in practice, Bitcoin finality is very good. There's never been more than like a 2-block proof of work and real. So it's essentially So you're layering this new technology, which gives us this kind of revolutionary thing, which is objective kind of trustlessness, and trying to put that on top of a permissioned kind of centralized system, so that you get that additional proof, that additional immutability, which there's no other way to get.
What's stored in those slots or the leaves of the Merkle tree? What's actually stored in those leaves?
So there's just people. So we construct the Merkle tree for this service, and people just send a commitment via an API.
So the commitment is stored in that way.
Yeah.
Okay.
And then you basically the kind of workflow is that you would, if you want to use one of these slots, you send a commitment. We then wait for all the other commitments. We construct the Merkle tree, the Merkle root, the Bitcoin transaction. Then when the Bitcoin transaction is confirmed, the user can then download the proof. So they better download the transaction ID, the Merkle path, and then they store that proof that they can then use, obviously, to prove their uniqueness.
And then the guard nodes, they're watching the chain on behalf of the sidechain.
Yes, that's another.
Are they also aware of what's happening on the sidechain?
So that's the idea of the guard nodes, is basically providing another layer of guarantee that nothing bad is happening on the sidechain. So the guard nodes can kind of observe any like invalid blocks, or if they see two sidechain blocks basically the same height that both signed, that means there's been a failure of the block signing mechanism. That should never happen, and so that they can then use that as proof, raise the alarm. So it's about the guard node idea of basically trying to incentivize more people to run fully verifying nodes.
Any other questions? No? I've just got a couple last ones then. So you forked elements. Are you backporting all changes that
Yeah, we
blockchain?
were, although we did have diverged quite a lot, and so we talked to recently. We've talked to Blockstream quite a lot. We've got quite good dialogue now, and they're keen for us to as a kind of for the I think they don't want elements to be a Blockstream project. They want it to be more of a kind of wider kind of project. So I think that'd be really good for us as well, if we can kind of take a lot of things we needed and actually add them to the main elements code base as like configuration options. It means that we can kind of focus on a we push back quite a lot of things back into elements, but yeah, and I think long term it would be much nicer overall if we just had a single code base essentially, and we didn't have to maintain a separate for. So that's our medium long term aim, is to go back to elements. And this project is quite unique as well. Some of the newer projects that we started working on are a bit different and are like real sidechains, as in like Bitcoin. So Bitcoin with a peg, which are more kind of elements suited. So some of the features that we added for DGLD are kind of quite unique. So we're thinking of, we've got a plan basically to merge in the things we need back into elements for this next project and just use elements.
And so this new project is more like Liquid? It's like a consortium?
Similar, yeah.
Okay, you go first, no problem.
So very quickly, if you can peg Bitcoin onto your sidechain, right? Does your current technology stack allow you to do something similar to what MakerDAO has done on Ethereum using the Bitcoin blockchain, collateralized by Bitcoin?
Yeah, there's probably something you could do to kind of replicate that.
Is that
It might be slightly complicated though. But there's probably some. I think there's some ways you could go about that.
robustly, or is it a bit of a hack?
I'm not sure. Maybe it's a bit of a hack. Yeah.
TBTCs that way. Just look at the Keep network. They're doing it.
Oh, are they on Bitcoin?
Yeah. So, how many signers are there in your federation?
In this, for the gold token, there's just we have 5 signing nodes. We have
Five.
three or five.
Three or
But
five.
But
So
these aren't. It's not like Liquid, where these are separate legal entities with their own protections. This is all these signing nodes are owned by the issuer. So the issuer is the company that owns the vault, owns the gold. Doesn't own the token holders own the gold in the vault, but the issuer is the entity which basically is responsible for the underlying asset. And so these 5 signing nodes are, you have 5 instead of 1, basically just for redundancy and security. But these are under the legal control of the issuer.
so they will never go offline.
Yeah, so you basically have 3 or 5, so 2 of them can go down, and you still got liveness. You still create sign blocks, but you'd need 3 of them to have their keys, kind of hacked.
Are these signers' keys are in a multisig or?
Yeah, so it's basically a 3 or 5 multisig which signs the blocks. But each of the keys is generated on a HSM.
So have you considered when you say the multisig, is that just a multisig or like the real multisig like within separate geographical areas with NPC or something like that?
Yeah, it's this multisig. It's literally the way Elements works is that basically blocks require just a number of signatures. So you define, the chain is defined by a number of public keys, which are in the Genesis block, and that basically defines what is a valid block. So you have in Liquid, for example, we have a list of 15 public keys, and you define a valid block as a block that's signed by 11 of these 15 public keys. But basically, so in this DGLD chain, it's 3 or 5, and they're in separate locations, but they're all under control of a single entity. So if the issuer did want to shut it down or apply policy, then they've got that control.
So who will take care of it? Like when the issuer decided to shut it down? So what is my
Well, that's
avenues
at that point, everybody's everybody has a proof of their ownership of the gold, and they can go and claim their gold back from the issuer.
Issue.
Yeah.
Okay.
And if the issuer is not cooperative, then they own a proof of their ownership
Two.
to the gold.
So who has the gold?
The issuer in their vault. In DJLG's case, it's a company called PAMP, who are
So PAMP
Gold
is the
refiner.
custodian for the gold.
yeah,
Right. So they need to honor the certificate from the issuers
yeah.
or from the customers. So if
Well,
the
they
issuer-
are the issuer of the token.
who the custodian of the
Yeah.
gold. Hmm.
What's the use case of having, so like I know it's a GIF up there, but like one party setting up a sidechain? Like if I get the liquid case because then you're moving Bitcoin between like
Yeah.
exchanges, and I kind of get the sidechain when you try and do like a regulated security token.
Yeah.
Like obviously there's all regulatory concerns around
Mm.
that, but like I kind of get if there's a bunch of security tokens all being issued on a sidechain. But why would you have one sidechain for each security token? Why wouldn't you have
Because
a
it-
sidechain and issue lots of security tokens on it?
Because of the verification cost, and I don't care about these other securities. I only care about one security. So it's this idea with Ethereum. So if I want to verify me receiving a token, or then I have to verify everyone else's tokens history, whereas I don't care about those tokens. So on Ethereum, if you issued the gold token on Ethereum and you wanted to verify that you'd received the token without trusting a server somewhere that you've actually received the token, then I have to verify the entire Ethereum blockchain, which contains every single other there's 100,000 tokens that have been issued on Ethereum.
No, but
And I don't care about
that's very
manipulation.
different. Like Ethereum, you're issuing all the tokens on chain.
Yeah.
With this, with the question I'm asking is you're issuing a bunch of tokens on a side chain. So you've
Yeah.
still got the same footprint on the
Yeah, but
blockchain as you would as if it was
If
one
I'm
token
interested
or
in,
multiple tokens.
if I verify the Bitcoin blockchain, so I'm interested in Bitcoin and my ownership of Bitcoin. If I'm interested in the gold-backed token, I want to verify my ownership of the gold token. And I don't want to have to verify lots of other tokens at the same time. But this model where you rely on Bitcoin's immutability, you have to verify Bitcoin and the sidechain you're interested in, essentially. And then you've got this proof of single ownership, this proof of immutability.
So let's say a credit union back in the US, if they want to just go for a stable coin or something like that,
Mm.
any credit union can actually put up the 1 billion. So a DAI is like about 100 million on supply. So they can be an issuer and they can put that money into some other deposit, one coin that is getting sold over the market. But then you have some kind of assurance from the Bitcoin as long as the Bitcoin exists. Even if we get, if that bank belly up at some time, you can actually go back to the issuer and say, hey, I got this.
Mm.
It's possible?
Well, yeah. I mean, you always, with any
Or
asset,
you will avoid the issue with the Tether and the Bitfinex.
Yeah. Well, you always trust the custodian, or whether it's dollar-backed stablecoin.
The dollar-backed stable coins are actually, you're trusting the guy, it's fine.
You're trusting the guy that's
But
he's
then
got the
they
dollar.
need to keep the receipt somewhere. The certificate that you're offering
Yeah.
is like the Bitfinex issuing the Tether, but the Bitfinex can take that money and then nobody can actually prove that they have taken the reserve belongs to Tether,
Yeah.
right? In this case, you can actually prove it. The moment that
You can attest the bank account number
Yes,
on the
yes.
sidechain. That's what he's
Yes,
talking about.
yes.
In the same way you have your vault location.
Right.
Okay. Yeah.
So you can actually prove it. So they
Well, you
can never move the money.
You can
with
prove
it.
someone's committed that information,
Right.
but I guess you need
The
some.
reserve cannot be moved.
Yeah,
That's
you
the
need
point.
some authentication from the bank that it's not moved, I think. But yeah.
just don't know whether it makes sense to like have a London Stock Exchange sidechain, or whether it makes
I
sense
guess
for
there's
everyone
trade-offs. I mean,
to issue their own security
The
token
real-
on their own sidechain.
Yeah, the real problem with one of our things we want to do is we want to make this it's easy enough. It should be easy enough to create your own sidechain as it is to launch an ERC20 token. In terms of the user experience of doing that.
Like a coin gen back in the day.
Well,
You can issue your own Bitcoin like a few clicks.
Well, yeah, exactly. Or you create your own. So you create your own token, but it's just the interface should be the same as ERC20, but the underlying cryptographic structure is not scalable in Ethereum's case,
Right.
and that you should only have to verify the history of the token that you're interested in. However, I mean, the big stumbling block with this kind of approach is integration. I mean, for an exchange to list an ERC20 token is very easy because they're already running an Ethereum node. So it's easy for an exchange to add another Ethereum token because they're forced to already have that information, on a node they control. So the issue, with kind of getting exchange integrations with this model is more difficult because you're asking the exchange to run a new blockchain client for every token, which they will not really want to do. So in terms of actual computational effort, in terms of the raw verification of the blockchain, it's more scalable. But in terms of the kind of setup and integration with exchanges, it's kind of more complexity. So I think this is really what we've got to work on next, is making this as easy as, say, adding an ERC20 token to an exchange, so that they maybe have some single daemon that they run, and this will automatically, connect to the particular token sidechain that they're interested in and retrieve the information.
Oh, slightly off topic here, but if you looked at using your sidechain just for validation of sort of banking derivative transactions between banks.
In principle, it's
just data instead of asset.
Yeah, of course. I mean, this is. You could do so many things with the Elements platform.
And then, I think the issue there would be you're going to have many different counterparties. They wouldn't want a single signer.
Yeah, you could have. There's lots of cases where you'd want multiple different signers with different trust kind of assumptions.
Yeah. And anyone, they can blow the whistle if they see any. It's almost like everybody becomes a god.
Yeah, of course. Yeah.
So you can always blow a whistle, but the issue with the blockchain is it's not how much you're losing, but it's how much you're gaining out of it. So it's a proof of work and proof of stake. It's off the topic, but I'm just blowing the whistle, right? Proof of work is like people put a lot of money. It's a very cash flow intensive business to validate the Bitcoin chain. So they have put a lot of money to get that as an initial setup to run this validation network, and what they're getting out is very minimal. The initial investment. So that's actually one of the pillar for security. So what you're actually getting, what you're losing, right?
Yeah.
So you blow the whistle, but you can only lose some money. But then people are not really interested to run that network.
Yeah, that's the challenge, right? It's running the network and validating. That's the hard part.
None of the ERC20 tokens were security tokens. They were just garbage, right?
There's lots
you
of these
had
other.
the ERC20 token, you had no rights.
Well,
whatsoever.
ERC20. Well, it depends what the definition of the token was. The ERC20 tokens are permissionless, so they can't be used for equities like in the US, for example, because you have to have rules applied to who can buy them, who can sell them. Most ERC20 tokens were just used as network tokens or utility tokens, not actual ownership of anything. You could have defined them in that way, but they're not very useful for that. The people have come up with all these other token standards like ERC 1404, which have whitelisting, but these seem really difficult. So you're actually doing whitelisting on chain, so the smart contract actually contains the whole whitelist.
They have to be regulated.
Yeah,
They're going to have them at all, they have to be regulated.
Yeah, of course, yeah. But I think this is these are kind of, I think, potentially useful constructions, but I think the scalability of Ethereum is going to be a big problem.
So sorry, so from your watchtower construction in the Bitcoin, can they verify if they made a timestamp?
Well, I mean, Bitcoin is not a smart contract. Like
No, the
most
relayer,
languages.
that you're building.
Yeah, for Bitcoin we are building a watchtower. For Ethereum we are building a relayer and it uses smart contracts.
Right.
So not sure what it is there. I mean, if they need a watchtower in a sidechain, probably we can think of doing a watchtower for that. But
Because they're always
like for any blockchain. like-
committing into Bitcoin, so they.
Okay, we'll wrap up. You can continue the conversation afterwards. Thank you very much, Tom.
Thank you.